Hello friends, here in this video we will see a derivation in which we will derive a formula for the condition when load is parallel to the axis of the bolt, and for that purpose here we have a diagram. Now in this diagram, this is a bracket which is connected to a wall or a ceiling. Now this bracket is subjected to load W, as can be seen here. Next, when this load acts on the bracket, there are chances of this bracket to move down. Here I have two center lines 1 and 2. At center line 1, the distance is L1 from the fixed point A. Next, center line 2, it has distance L2 from the fixed point A, or we can say the fixed edge. Now at these centers there are two bolts, as can be seen from the other direction. Like for example, on center line 1 there would be 2 bolts, on center line 2 there would be 2 bolts. So in total in this problem we have 4 number of bolts. So now here we have to derive the formula, and for that formula what we have to understand is that when the load is acting, there are two kinds of possibilities. First, because of this load, both the location at center 1 and center 2, the bolts which are present, under the action of this load, the bolts can stretch. They can stretch, that is, they are in tension, and then they would be failing. So once the load is acting, the primary effect is this load would be shared equally by all the 4 bolts, and all of them, they would be stretched and failing under tension. So here first of all I'll say that since primary tensile load will be the primary tensile load, I'll denote it by W suffix T1, and it will be equal to load divided by N, where I'll say that N is the total number of bolts. Now this I will keep it as equation number 1. Now after this I'll say that therefore N is equal to number of bolts, and from equation number 1 it is clear that the total load is shared by N number of bolts. So primary tensile load will be on each of the bolts. So I'll write down therefore primary tensile load will be equal for all the bolts, and because of the primary tensile load, the bolts would be failing under tension, that is, they would be stretched and then they will fail. That example we can say it is like here. If I draw the diagram and explain, like for example, this is a bolt, and when the load is acting, it is subjected to tension. This bolt will get stretched, the length will increase, diameter will go on decrease, and it will fail, something like this. Now when we have considered primary tensile load, after that I'll write down now because of primary tensile load, the bolts will be failing because of pure tension. So when we are considering the primary tensile load, in that case we can say that the bolts would be failing only because of tension. Next, after this I will consider the secondary tensile load. I'll write down considering secondary tensile load. Now what is the meaning of secondary tensile load? Now suppose the load is acting and these bolts, they are not failing together. That is, in the first case when it was primary tensile load, all the bolts, they were failing together, they were getting stressed together and then it was breaking. But here when we are considering secondary tensile load, because of this what happens is when the load is acting, there are chances of out of both the bolts, any one of the bolts are stretching more compared to the other. Now how this takes place? For that I will write down considering secondary tensile load. Now I'll write down because of the load there are chances that the bracket will tilt about the tilting edge AA. Now what is this? Here there are chances that this AA is called as the tilting edge, and about this the bracket it can tilt. When the load is acting, the bracket would be tilting. One of the bolts which are stronger, they would be in contact with the tilting edge, whereas the other bolts, they will try to come out, and finally these bolts, they would be stretched so much that they would be failing. So this is the effect of secondary tensile load, that all the bolts would not fail at the same time, but those bolts which are stronger will remain in contact, or we can say they will deform less as compared to the bolts which are moving continuously and they are in tension. Now after this, here I have written because of the load there are chances that the bracket will tilt about the tilting edge. Next, the bolts which are far away from the tilting edge or which are closer to the load will be more heavily loaded. So here I have written that the bolts which are far away from the tilting edge, if you compare 1 and 2, the bolts at center line 2, they are far away from the tilting edge or they are closer to the load. So these bolts which are closer to the load, they would be failing more or fail more heavily loaded. Now after this I can say that the bolts which are closer to the tilting edge will be less loaded. Now, here as I have written that the bolts which are closer to the tilting edge will be less loaded. So we can see in the diagram that the bolts at center line 1, these are closer to the tilting edge A. So these bolts would be less loaded compared to bolts at center line 2, because at center line 2 they are far away from the tilting edge and closer to the load. So the bolts which are far away from tilting edge and closer to the load, those bolts would be heavily loaded, more load would be acting here, whereas the bolts which are closer to tilting edge and far away from the load, like at center line 1, these bolts would be less loaded. So here I'll assume one term, that is let small w be load on each bolt per unit distance. Unit will be Newton per mm. So next I can say that if W is the load on each bolt per unit distance, if the unit distance is L1, then the load on bolts at section 11, therefore load on each bolt at distance L1, that we will denote it by W1 is equal to W into L1. This much is the load on bolts at center line 1, and this is the load on one bolt. Now once we get the value of load on a single bolt, then I can take the moment of this load about the tilting edge A. So I'll say that therefore taking moment of this load about tilting edge AA. So when we are taking the moments, it will be therefore M will be equal to W into L1, this is the load, multiplied by distance is L1, so again I have to multiply it. So finally the moment becomes W into L1 square. Next I'll say that similarly load on each bolt at distance L2, that will be W2 is equal to small w into L2, because small w is the intensity of load on each bolt per unit distance. If we want the load on bolts which are at distance L2, so we have to multiply W by L2, as I can explain it with the diagram here. If I want how much is the load on distance L2 on each bolt, that will be small w multiplied by this distance. Next I will take the moment, therefore taking moment of load at L2 about the tilting edge AA. Now here if I take the moment, M will be equal to W into L2, and the distance from the tilting edge is L2. The load on bolts at section 2 and their distance is L2. So W into L2. So this becomes W into L2 square. Therefore, total moment is given by total moment M will be equal to, for the first load we were getting the moment as W L1 square. For the second bolt we are getting it as W into L2 square. Now these are the moments of the load on bolts which are single, means at L1 we are assuming one bolt, at L2 there is one bolt. But suppose if there are two bolts, I'll take the example that therefore assuming 2 bolts at each L1 and L2 respectively. So therefore total moment now will be equal to 2 bolts, so it is 2 into W into L1 square plus 2 into W into L2 square. So here I can take 2W common. Into the bracket we have L1 square plus L2 square. This will be equation number 1 for us, or after, I think equation 1 has been given. This will be equation 2. Now, after getting the moment or because of the load on the bolts, I have taken the moment. Now I'll take the moment about the entire bracket, that is the moment, the load which is acting at the bracket. I'll take the moment. This will be capital W into L. So after this I'll say that therefore taking moment of load capital W about tilting edge AA. So therefore M will be equal to W into L. This I will call it as equation number 3. So now after getting equation number 3, that is here I have taken the moment of total load about the tilting edge. Next, from equation number 2, here also I was getting total moment. In equation number 3 we are getting total moment. In equation number 2 the total moment was because of the load acting at each of the distances L1 and L2. This total moment in equation 3 is because of the load acting on the bracket. So here I'll say that therefore equating equation number 2 and 3. So therefore in equation 2 we were having 2W L1 square plus L2 square. In equation 3 W into L. So here I will keep small w on one side. So therefore small w will be equal to W into L upon, here I have 2 into L1 square plus L2 square. This will be equation number 4 for us. So therefore from equation number 4, load per unit distance on each bolt can be found out. So here we have equation number 4. From this equation we can calculate how much will be the load on each of the bolts. Now if we look into the diagram, bolts which are at section 1, they have less chances of failing because they are far away from load. At the same time they are very close to this tilting edge. Whereas bolts at section number 2, the chances of failing here are more because they are closer to the load, at the same time far away from the tilting edge. So after this I'll say that bolts which are far away from tilting edge AA will be heavily loaded. So therefore we would be designing the bolts at section 2. So hence I can say that therefore load on bolts at section 2, or we can say secondary tensile load denoted by W suffix T2 will be equal to small w multiplied by L2. So here I have the equation. Small w is the intensity of load per unit distance, and if we want the load on distance L2, I have to multiply by L2 here. So finally secondary tensile load will be this W value we have got, it is capital W into L upon 2 into L1 square plus L2 square multiplied by L2. So here I can say that this will be equation number 5. So equation number 5 gives secondary tensile load. In equation number 1 we were having primary tensile load on each bolt. In equation number 2 we are getting secondary tensile load on each bolt at distance L2. So after this I'll say that therefore total tensile load, I'll denote it by W suffix T, and this will be equal to WT1 plus WT2. These values of WT1 we can get it from equation number 1 and WT2 we can get it from equation 5. Now after getting the total load, since bolts they are having threaded section, so I can say that therefore tensile strength of each bolt will be tensile strength, it is W suffix T, that is the load carrying capacity we can say, or tensile load, that will be area multiplied by tensile stress. Now how to get this area? Since we know that when we have bolts they have threads, bolts are having threaded section, so here we would be getting this small area because of the small diameter DC and a bigger area because of the outer diameter DO. So now bolts would be failing about the core diameter because here the area is less, it will be failing at the core. So I'll draw the failing area. It will be a circle, circular in section, having the diameter as d suffix c. So this is the resisting area. So therefore WT becomes, area is area of a circle, pi by 4 dc square into sigma t. Here I'll keep this as equation capital A, and therefore from equation number capital A, DC, that is the core diameter, can be calculated. And once we know the value of core diameter, we can even calculate the outer diameter by using the relation DO is equal to DC upon 0.84. And in this way we can design any of the bolts. So here in this video we have seen that when the load is parallel to the axis of the bolt, how much is the load acting on the bolts, which are the bolts which are heavily loaded, which bolts are less heavily loaded, how to design that bolt, get their diameters, that we have seen in this video.